Hello, everyone, and welcome. This is Chen Fang. I'm going to talk about linear expected complexity for directional and multiplicative Voronoi diagrams. This is joint work with Ben Rachel. Voronoi diagram is a basic data structures in computational geometry. Also has many applications like in ESA label, motion planning, and polylocation. Voronoi diagram is a partition of space into cells such that every point in a cell shares the same closed set. Let's review some basic concepts in Voronoi diagram. For every input point, P can consider as a set. Then the bisector between two set P and Q is a set of points equidistant to set P and Q, like in this figure. For two set P and Q, the blue line. Every point in this blue line has equidistance to P and Q. Also, for a set P, the Voronoi set of set P is a set of points for the closed set is set P, like in this figure. For every point in this green area, for the closed set is P. So the green area is a cell, Voronoi cell of set P. So the Voronoi edge is maximum bisector portion adjacent to the two cells. And the Voronoi vertex is the endpoints of edges, which has equidistant to at least 3 sets. And the Voronoi diagram then is a collection of edges, vertices, and faces. And it has linear complexity in the plane since it's a planar graph, and each set has exactly one face. There are many variants of Voronoi diagram, changing from distance function or the sets. In standard Voronoi diagram, the complexity is linear, and the distance to a set is equidistant. For additive Voronoi diagram, the complexity is linear, and the distance to a set is equidistant plus a constant. And if we change a Voronoi set from a point to a segment, then the distance to a set is a closed segment set, and it still has linear complexity. However, some variants may have worst-case complexity be much higher. For multiplicative Voronoi diagram, the complexity is quadratic, and the distance to a set is normal equidistance times a constant weight. For semi Voronoi diagram, the complexity is also quadratic when the set is visible to some random half plane. For Voronoi diagram, untitled, still the complexity can be quadratic based on the geodesic distance. For high-dimensional space, the Voronoi diagram complexity can depend on the input dimension D. We want to argue that the expected complexity of multiplicative Voronoi and semi Voronoi diagram is linear for some certain randomness assumptions. And first, let's consider the semi Voronoi diagram. In standard Voronoi diagram, each set can see the entire plane. However, that always happens if we consider a camera or a human as a set. Then each of it, then a camera or a human can only see some restricted view angles, not the whole plane. As in semi Voronoi diagram, each set P is visible to some given half plane HP, and the distance between a set P and a point Q is infinity if Q is not visible by HP. Otherwise, the distance is normal equidistance if Q is visible by set P. In understanding the semi Voronoi cells, we give a figure. In this figure, there are two Voronoi sets in the left semi Voronoi set is visible to the right half plane, and the right side is visible to the left half plane, and each of it control two disjoint cells. And this non-local behavior may lead to quadratic worst-case complexity. Now we demonstrate an example to show that the semi-Voronoi diagram has worst-case n-square quadratic complexity. The worst-case design is as follows. At first, we put n sides on a horizontal line, LH, and each is visible to the half plane above that line. And then we put another n sides on a vertical line, and each of for the visible area is just the half plane below it. The construction to make every side on this horizontal line can control n disjoint cells. So the total number of cells in this construction will be n square. And the quadratic complexity was first shown by a paper in 2014. So if the worst case is bad, a common strategy is assume some randomness. Then look at the expected behavior. We consider the random semi-Voronoi sets. For a fixed set position Pi, the visible half plane HPi is sampled uniformly from all the half planes with bounded line passing Pi. Look at the figure. The bounded line of a half plane passes through set Pi. So to produce a random half plane, first we sample a random line Li through Pi over all the possible directions. Then we just pick one side of Li with 1/2 probability. In fact, we already need a less randomness model. In this model, every set locations are fixed. Also, the bounding line for each set Pi is also fixed. The only randomness here is that which side of Li to be visible by Pi is 1/2 probability. The main results at here is that we get n log cubic n complexity with high probability. By using a candidate diagram approach, our previous paper, we also refine that approach to get the optimal expected linear complexity. In our approach, the high-level idea is like here. We partition the plane into alpha cells, and alpha is the number of cells. And each cell guarantees that the semi-Voronoi diagram only involves at most beta directional sites. Then the only beta square worst case complexity in each cell. Then the total complexity will be alpha times beta square. So what the diagram can be? Intuitively, the least visible semi-Voronoi set should be one of the beta least sites, equal directions. If beta is large enough, so look at the beta order Voronoi diagram. The definition is that each cell has the same beta least sites, and it has n minus beta times beta complexity. That means we partition the plane into n minus beta times beta number of cells, and each cell has a worst case beta square complexity. So the problem is how big should beta be? For each point Q, the probability Q is visible by one of its beta least directional sites is 1 minus 1 over 2 exponential beta. The explanation is as follows: because Q is visible by each set with 1/2 probability independently, so Q is not visible by any of beta sets with probability be the product of 1/2 by beta times. Then calculated complement should be 1 minus 1 over 2 exponential beta. So the arrangement of bounded of half plane of beta sets has betas or beta square regions. The points in a region have the same group of visible sets. So by unibound over beta square regions, the entire plane is visible to beta sets with the probability that 1 minus beta square over 2 exponential beta. If beta be some constant times log n, then the probability will be 1 minus 1 over n exponential to the c, which is high probability. So we partition the space, the plane into O(n) log n cells with log n of the Voronoi diagram, and we get the semi Voronoi diagram has a complexity be alpha times beta square, which will be n log cubic n complexity with high probability. And we show that by using more careful analysis, we will produce expected linear complexity. The intuition is that not all the cells don't need to have the same number of candidates. And for different cells, the number of candidates can differ. And we can partition the space progressively. And first, we compute the first order Voronoi diagram of sets, which divides the plane into n cells and label each of them B1. Then, for a given cell, C is label 1. For example, a cell with blue boundary. If it is not covered by its nearest set, then compute the second order Voronoi diagram in set C and label each subcell with label 2. If a given cell with label 2 and is not covered by the two nearest sets, we compute the third order Voronoi diagram. For example, in the figure, the cell with red edge with a red boundary. Then we calculate the third order Voronoi diagram and inside that cell, and label each subcell to be 3. This procedure will follows, and until each cell has a final label. If a cell has label J, that means it is covered by the J nearest sets, but not covered by J minus 1 nearest sets. So, to bound the expected complexity, let alpha I be the number of regions with label I. Then the expected complexity of semi Voronoi diagram will be expected alpha I times I squared. Then, after a bunch of calculations in this paper, we will show that the expected complexity will be linear. Then we consider multiplicative Voronoi diagram. In this diagram, the distance from a point Q to a set P is the normal distance times the weight of set P. In many applications in biology, social network, the different sets can have different signal strings. That's the original motivation to give different weights to different sets. And it has n square quadratic complexity. However, if the weights are randomly permuted, a previous paper shows that it has expected n log square n complexity. By refined candidate diagram approach again, you can get that For a set of n-weighted sets, for the locations are arbitrary, and each set samples its weight from a weighted set with constant size, then the expected complexity of multiplicative Voronoi diagram will have complexity of n times c to the exponential 6. If c is a constant, then the expected complexity is linear. Then we consider the weighted Voronoi diagram with sampling location, and for each set, the weight is arbitrary, but its location are sampled in a unit square. We partition the unit square into n equal size grid cells. If in each cell, you can argue that the complexity is constant, then the total complexity is linear. A high-level idea is that, in order to argue that the complexity of each grid cell is constant, for any point y in the grid cell, we transfer the weighted VD around y to be unweighted one by stretching the sets. For a set S with weight W and distance d to y, which can be considered as a set T with weight 1 and distance W times d to y from the range from y through S. After that, then set T can be considered as an unweighted set. After that, we divide the unit square into around the cell, grid cell y to be annulus. And we want to analyze the expected number of stretched sets in each annulus for the contribution to the Voronoi diagram inside of grid cell. If I is small, the area of annulus I is small, then it contains a small number of stretched sets, since the sets are uniform distributed. If I is large, then any stretched set P in this annulus is likely to be blocked by some stretched set Q, which is closer to Y. That means its contribution also can be bounded. For this basic plan is a bit tricky, and we put our third result that S be a set of n-weighted sets whose location are sampled uniformly at random from a unit square. The expected complexity is linear. For more detail or questions about this paper, please contact me or other author, Ben Rachel. That's all. Thank you.